Okay, the problem, CA dot CB equals A dot B times C. And what you're asked to do is determine whether that's true or false. There are a couple of ways to see this. If you're really familiar with dot products, you could just maybe do an example. 2 times the vector 3i plus 4j dotted with 2 times the vector 5i minus 3j. Okay, do you get 2 times the dot product of those two vectors? You don't. You get 4 times. And you see why if you do this in symbols. You need to learn to do this stuff in symbols. So let's just take, okay, what we've got here are 3 unrelated assertions. Okay, CA dot CB equals A dot B times C. CA dot C times A dot B equals CA dot CB. Does the C somehow distribute through here? And CA dot B equals A dot CB. Now, one of those 3 is true, and only one. We only look at the first one right now, and we look at it 2 ways. We look at it geometrically in terms of projections, because that's what dot products are kind of all about, and we look at it in terms of just symbols. Okay, in terms of symbols, which you probably find easiest, projections you find more informative. But in terms of symbols, let's assume that these vectors are in 2 dimensions, because as we'll find out, whatever happens in 2 dimensions can probably be extended to higher dimensions. Okay, so let's let A be A1I plus A2J, and let B be B1I plus B2J. Then CA dot CB is C times the A1I plus A2J, and CB is C times B1 plus I plus B2J. Okay, if we dot this with this, well, we haven't done the dot product yet. First I'm going to distribute the C through here, and I'm going to distribute it through here. So this is going to give me CA1 times the I vector plus CA2 times the J vector, and we're going to dot that with what we get when we distribute C through here. It's the CB1I plus CB2J vector. When we do that, it gets a little bit sloppy down there. We get CA1 times CA2 plus CB1 times CB2. And what's that going to equal? Well, that's going to equal C squared times A1, A2 plus C squared times B1, B2. Okay? And now we want to see if that's equal to what we get if we do the right-hand side, where we just do the A dot B and multiply by C. Well, if you write that down and write it out, you'll see that you're going to get just a single C. You're not going to get any C squareds. Whereas down here you always got a C squared, 1 from here and 1 from here. On this side you're only going to get a C. Now you need to write that out. You need to look at how the book writes things out and so forth. But that's a strategy that you can always use. Okay, just replace A by A1I plus A2J, B by B1I plus B2J, and write out what these things give you. And see if the 2 sides come out the same, and then think about it. Another way to look at it, okay, here's A, here's B. Okay? Now, the dot product is related to the projection. Okay? And the dot product is the projection of A on B, the magnitude of the projection of A on B, multiplied by the magnitude of B. Not exactly what I said, because if this projection is negative, you're going to get a negative result, but you can see what I'm talking about. Okay, you have to kind of think about that part, but let's just assume that the projection of A on B is in the direction of B, so we don't have to worry about a negative sign. And then, do the opposite, worry about the negative sign. Okay, well, we take this projection here, the magnitude of this, times the magnitude of this. It's just the area of a rectangle whose one side is equal to this, whose other side is equal to this. So the area is A dot B. At least it's the absolute value of the magnitude of A dot B. Again, if this goes in the opposite, if you're past 100, if you're past 90 degrees here, you're going to get a negative for your dot product. The area of the rectangle that you get when you do this magnitude times this magnitude is still going to be the same. Okay, well, what happens now if you, let's say, double the vector A and you double the vector B? Well, that's just going to make this picture twice as big. This projection is going to be twice as big. The B vector is going to be twice as big. So your rectangle is going to be twice as wide and twice as high. Now, how many more times area is it going to have? Okay, well, you should think about that. Somebody said twice, and somebody, along with most of the other universe that comes out of our public schools, doesn't understand proportionality very well. If you double the dimensions of a rectangle, okay, this gets twice as high and this gets twice as wide. Well, here's your original size. If you've doubled everything, you can divide this doubled rectangle into 4 rectangles, each of which has the same area as the original. So when you double the dimensions, you're quadrupling the area, okay? And you can also understand that if you have C times the dimensions, well, this gets C times as big, this gets C times as big, so that the product of these two things gets C squared times as big. So you want to be able to think in terms of geometric arguments as well as algebraic arguments. There's a contrast between a geometric interpretation and an algebraic interpretation. You're going to do much better if you can do both. But if you can do at least one, whichever one's more obvious to you, it's sufficient, okay? And if you're struggling to keep up, sufficient is good enough, and I don't expect a miracle of binocular vision where you see it both ways. Although that miracle would be very beneficial to you, and I hope someday you achieve it, and I hope right now you achieve it. One or the other will usually suffice and will certainly be enough to get you by in this course. Okay? Well, that's just an outline of how you do these. Look at how these sorts of things are addressed in your text as well as how I address them here.